My name is Ju. I was born in China, so I know everything about noodles and dumplings. I grew up most of my life in Italy, pizza, pasta, all about that. And now I've been living in the UK, so yeah. Anywho, you can find me online as Arkham with a 4. I'm currently on my paternity leave, so this is my daughter. Thank you. These are the parents, basically. So I just want to start with a super short history of cryptography. If you know everything about cryptography, you can just fall asleep for the next 5 minutes, and then I will wake you up. So I will, come and drag you back into the talk when I'm done with this super short history of cryptography. I just want to make sure that, I don't lose anybody on the way, right? So cryptography, 2 Greek words, kryptos, which is hidden, graphia, writing, is the art of writing secrets. You take the secret message that you want to send, you encode it and encipher it. So you turn plain text into ciphertext. You send it over some sort of insecure medium. It could be, a letter. It could be a chest. It could be the internet. And someone at the other end of the world just knows somehow what you've used to encipher the message and decodes it or deciphers it, right? People have been doing it for centuries. Actually, not for centuries, for thousands of years, yeah? So Caesar cipher, they say that Julius Caesar used to use this. You take your message, you take each letter, and you move it by 3 positions, right? So if you want to write et tu Brutus, you just take E, and you do E, F, G, H, and you so on and so forth for each other letter. And then you send this big blurb in a letter. Nobody can read it. Somehow, magically, at the other end, someone knows, oh, I just need to do the opposite. They reverse the Caesar cipher, and you get back the original message. I didn't say this, but feel free to interrupt me at any time if there's anything that you don't understand. And I don't think we have a microphone, but you can just yell. I will repeat the question here. There is a microphone. I stand corrected. Right, Caesar cipher. As you can probably tell, this is not the most secure cipher because there's basically 26 possible offsets. So once you know that this is the ciphering technique, it's quite easy to break. And people, they've been smart for thousands of years. We're not the first smart humans. So what they thought about is, well, what if I just create a completely random mapping? And I just decide, wherever I see a letter, I just replace it with another random letter. And this way, this mapping becomes the shared secret. And I can send my letters over an insecure medium. And whoever shares the secret with me will be able to read that message. If you don't know the secret, it's completely impossible for you to read it. Well, not in this case. As you can see, there's a glaring weakness in my completely random cipher. Okie dokes. So imagine we want to send this famous piece of plain text. And you just get this blurb. Whoever knows that this was the substitution algorithm, they can just put it back on reverse and get the message, right? So if you think about it, this is pretty secure, right? If you don't know what is what, it's really difficult to brute force this thing, right? Except there are a couple of problems. First of all, spaces. If you keep the spaces in the ciphertext, and you know that the original message was in English, there are not that many words in English which are composed by 2 letters. There's up, at, if, right? So you can write down all the 2-letter words in English, and you can just try them. And imagine we know that FK is up. Now we know that F is U, and K is P, right? And we can use this information to try to propagate this thing in the ciphertext and see if other patterns emerge, right? And so on and so forth. Then you break the 3-letter words, you break the 4-letter words, and it helps so much when you know who is sending the message. For example, if it's a weather report sending messages, you probably know that the 4-letter word is rain or cloud. You know, it helps so much to know what the person is trying to write. But fortunately, this fix is quite easy. You just remove all the spaces. So for whoever is trying to intercept a message, it just becomes a huge blob. If instead you have the secret key, once you decode it, there's no spaces, but in a way or another, you can still see the words. It's not that difficult. That was the first problem, spaces. Okay, we fixed that. The other problem is called frequency analysis. This graph indicates the frequency of letters in the complete works of William Shakespeare. So you take all the works of William Shakespeare and you start counting all the letters, and this is the result. As you can probably tell, if you can't tell, this is the column that says E, and E is the most common used letter in the English language. So imagine you have this mangled ciphertext, and for some reason, the most used letter in that ciphertext is Q. You can pretty much guess that the Q in reality is an E, right? And this is something that was known to Arab mathematicians in the 6th century. So like more than 15,000 years ago. Oh, no, sorry, 1500. Close enough. And anyways, like once you do that, you know that Q is E, then you can move on to the next letter, and you can try saying, okay, if it's not E, it's probably T, or it's A, or it's I, or it's O, right? And you can do this for every language. You can do it for Polish, probably it's W, the most used letter in Polish. Anyways, and you can do it for Italian, for Spanish, for French. For each language, you just grab the Bible and do this thing on the Bible, and you'll get a very similar sort of like fingerprint of the language. And there's no escaping that. That is the language in one way, right? And yeah, there's basically no fix for that. So this is how a language is. And if you use a mono-alphabetic cipher, which is where you just have a single alphabet, this is a problem, right? But as you know, humans have been sneaky and very smart. For centuries, they've been inventing new ways of sending secret messages. I don't have time in this talk to talk about all the different ways that we used, but if you are curious, you should read this book. It talks about Julius Caesar. It talks about Mary, Queen of Scots, how she was caught because she sent a secret message in a broken cipher. It's really interesting. And it talks also about the Enigma Machine. Yeah, read this book. So yeah, we're going to skip forward 1,000 years. We're going to talk about the meat and potatoes of this talk, which is the Enigma Machine. Okay, so at the beginning I said, if you know cryptography, you could fall asleep. Now it's time to wake up again. I've said all the boring stuff. The Enigma Machine was invented by this German engineer in the 1920s, and I think he struggled to sell it at first, so nobody wanted to buy it. In the 1930s, some companies started to use it to send commercial secrets, so banks, or probably modern hedge funds and stuff like that. But when the Second World War started, the Wehrmacht, like the German army, the flying things, and the Navy, thank you, they started using the Enigma Machine to send secret messages. And it was basically the de facto standard in the German army to send secret messages. What I really love about the Enigma Machine is that it had a battery, but basically all of the machine worked in a mechanical way. The only thing that the battery did was to light up some light bulbs. So all the machine was completely mechanical, except that these light bulbs were lit up by a battery. we will see in excruciating detail how the machine works, don't worry. And what the machine did, which is spectacular, is that before we said that mono-alphabetic ciphers are really easy to break, right? So we just discover more or less the shape of a language and you just break it instantly. What the Enigma machine did was to create a very easy way to encipher a message using multiple alphabets. And by multiple alphabets, I mean that every time you press a key, one of those rotors, which you can see here at the top of the machine, one of them would rotate. And by rotating a rotor, you just switch to a completely different alphabet. So every time, imagine you're typing food, and these 4 letters, this means that each one of them is enciphered by a completely different cipher, which made it really, really hard to break using traditional techniques, right? Like using linguistic techniques. Like I think at that time in history, people were still trying to use philosophers or writers to break ciphers. And I think this was one of the first times where they understood that had to use mathematicians or puzzle solvers or statisticians. Cool. So I said that the cipher changes at every key press, but I really want you to understand in deep detail how the machine works, right? So we're going to open the machine. Amazing. You see, we have this keyboard, like our keyboard, not much change there, apart it's like a QWERTZ instead of a QWERTY. Right above the keyboard, you can see these little light bulbs. These are the things that the battery is lighting up. And now you just see the light bulbs, but they had this little transparent cover, which would just lit up, right? The part which is closer to us, this is called the plug board. And you can imagine that you had 10 cables which you could use to connect 2 pairs of letters. So at the beginning it will be completely empty, and then you can connect, let's say, Q with R. So every time you press Q on the keyboard, you're actually sending R to the machine. So it's a way to have even more, key space. So this is the plug board. You have these 10 pairs. Over history, they changed how many pairs of cables you had, but I'm not going to talk too much about that. What I want to focus on is at the top. You can see there's 1 rotor, another rotor, and a 3rd rotor. And then we have this little thing. I'm sure you won't be able to see it from there, but it has a little red B, and this is also another important bit. So basically the mental model that they want you to have is that whenever you press this key, it goes from the keyboard to the plug board, then it goes all on the back of the machine. It goes inside this first rotor. It somehow moves to the middle rotor, somehow moves to the leftmost rotor, then goes into this little box. It's sent back. So it goes back again into this rotor, all the way back to the middle, all the way back to the first. Now it's sent all the way back to the plug board. It goes through against these cables, and then finally it goes to light up that light bulb, right? I know that's a lot of words, so I'm going to show you a summary later. But this is how a rotor looks inside when you explode it, right? You can see like it's this big mess of cables, right? And I think when I was doing some research on this, like I've been doing programming for such a long time that I think, oh, it's sending a value, this cable, like it's sending X and it's receiving C. But there's no such thing. It's just, electric circuit. It's just like an offset. There's nothing there about values. It's like a purely, archaeological sort of thing. Anyways, this is the machine. It's exploded, and this is a little summary of what happens every time you press a key on the machine, right? You start from the keyboard, go through the plug board, go through the right wheel, middle wheel, left wheel, reflector all the way back to the left wheel, middle wheel, right wheel, go through the plug board again, and go through the lamp board, right? Cool. So I mentioned that the machine is only mechanical. So how does it actually work? I think I struggled for some time to really understand under the hood how the machine works. So I found this amazing YouTube video by, I think his name is Jared Owen, and he made a 3D reconstruction of the machine. And I'm going to show you a very short fragment of this video, but I think it's amazing. Let me just remove the annotations. There's no audio, so don't worry about that. Sorry. Okay, I think I managed sort of to do what I want. So yeah, this is the Enigma machine. You see, like, at some point he will press, yep, we have this thing open. So imagine if we remove all this stuff, we remove the keyboard, we remove the lamps, what's actually inside? The keys are standing on this piece of metal, right? Like that keyboard that we see. Each key on the keyboard is attached to this big piece of metal. And there's a little joint, you can see it here, where this bar rests. So every time you're pressing a key on the left-hand side, the right-hand side goes up. It's like, you know, a swing, basically. And every time you press it, the other part goes up, right? You press O, and the right hand goes up. Why is this useful? Because at the back of this actuator bar, there's like these 3 little hands, right? And you can see these 3 little hands are touching those rotors. So imagine every time you press a key, this part goes up, and it pushes the rotors in some direction, right? But there's also a really interesting way that these rotors are moving, right? Because if you look about it, only one wheel is working. And this is because the first hand, as you can see, is always touching the first wheel. So every time you press a key, the first wheel is rotating. And that's why the first wheel is also called the fast wheel, because at every time you're pressing the key as the operator, that wheel is moving. Okay, I thought the video just died, which would be unpleasant. Okay, so you see, every time you press, it just moves. You press and you move. But the problem is, like, if this was the only thing the Enigma machine did, you'd only have 26 combinations. So you're not doing better than the Caesar cipher, right? So you have to have a way to move the other wheels as well. And the trick is this. If we start looking at the second hand, we'll see something interesting, which is that the second hand, by default, is not moving anything. You can see it's like hitting against the smooth part of the wheel. So normally, it doesn't do anything. It is not allowed to move the middle wheel. So every time you press, only the fast wheel is moving. But eventually, the hand will fall into this little pocket that the rotor has. And once it's able to fall into that pocket, it will be able to move the middle wheel. And you can see it. Maybe I can go back a little bit. No, maybe a bit more. Yeah, okay. You can see that little pocket there on the red, right? So you can see that as the fast wheel moves, eventually that little hole will like be in the right place so that the second hand can go inside it and push the middle wheel as well. Puck. And you can see it moved the middle wheel, but also the first wheel. But as we said before, the first wheel was moving anyways, because that's the wheel that's always moving. So it's actually not doing anything with regards to the fast wheel, to the first wheel. But the thing which it is doing is it's also moving the middle wheel now. So we've just incremented our key space to 26 by 26, right? Like around like 600 combinations. I'm going to drink some water. And you can see it just goes back then to the normal operation where only the fast wheel moves. And as you can see now, the middle wheel has another little hole just in the same way so that we can push the last wheel, right? Just like it's like the same trick. So you see, whenever then the middle wheel falls into the same hole, the third hand will be able to push the last wheel, right? But I think this is a great lesson in unforeseen effects of your design, which is that, unfortunately, I don't know if you saw that, but when that last hand falls into the hole, it also pushes the middle wheel. And that was a mechanical bug in how they designed the machine, because effectively it reduces the key space of the middle wheel by 1. So instead of having 26 different sets, it only has 25. And in later versions of the Enigma machine, they fixed this mechanical bug. But in my version, which I've made for fun, I've kept this bug because I think it's quite cute. And in the literature, it's called double step, this mechanical bug of the machine. So I'm just going to do an instant replay for you, like they do, in football. So once that thing, you see, like all 3 wheels move. So we know that the first wheel would move anyways, right? But we do not expect the middle wheel to move. That should not move. But due to this mechanical bug, it does move. Well, whatever. Okay, so yeah, I'm not going to talk more about this video. Those little pink things are quite nice as well, because they just ensure that even if you press it a bit more, the wheel goes back into a known place. But yeah, you can watch the whole video. It's like 20 minutes, but it's really, really good. Okay, let me go back to the presentation. Any questions so far? I can show the video again if there's some questions. Yes? No? Yeah? I can see some legs moving, but no hands. Okay. Enter full screen. Okay, so now I want to do a little section where I pretend to be one of these German operators which would use the machine every day, right? You can see, like in this picture, there's like this field marshal like standing over you, so you better know, not make mistakes. And you can see like there's like many people, like because usually needs to be one person which is keying on the machine, and the other person which is writing down what the machine is emitting as output, right? So you always needed 2 operators, one which is pressing the key, and the other one which is writing down the results. And I think the third person is the person transmitting the things, in Morse code. I don't know what the guy on the back is doing, probably just watching. Okay, and this is a sheet that was used by the German army. I'm not sure if you can see it, but on the top left it says Geheime Kommandosache, which means secret command operation. So yeah, better not leave it on the bench or somewhere. And it's a sheet that contains the codes for a full month. So you can see like the first column is date. It goes from the 31st till the 1st. So usually every month they had a new sheet. And the way that we have this is there were spies and people, stealing these things. There were also what they were called pinch operations. So maybe they were able to sink a ship and get inside the ship before the sailors managed to destroy the secrets. So they were able to grab this code sheet for the month and send it back home for people to look at. Right? And you can see that it says, okay, for this day, you have to use these wheels. So they at some point, had 7 wheels to choose from, right? So you had this collection of 7 wheels, and the same tells you to use number 4, number 5, and number 1. Then there's this thing which is called the ring setting. So you can imagine each wheel had a pin that you could unlatch, rotate, and latch again. And this way, each wheel had another 26 possible configurations. And then you can see this pair of letters. Maybe you can't see it, but yeah, oh, look at that. You can see, K, L, I, T, F, Q, all these things were the plugboard settings. Yeah, you're supposed to connect K with L, I with T, F with Q, and so on and so forth. Great. Awesome. So basically, imagine you're this German operator, and the way you do your job every day is that you open the code book, you choose the rotors, you unpin them, put the right setting, put them inside the machine. At that point, you plug these 10 pairs of cables into the front of the machine. And at that point, you're ready to start sending the messages, right? I think in modern cryptography, like this is something we do as well, is that we know that we shouldn't be using the same setting over and over, because the more we use the same settings, the more we can give hints to who is trying to break the cipher. Like if you ever had to do like OAuth, right? You always use 2 different tokens. And they did the same. So they wanted to have a mechanism to use a temporary key to encipher this current message, and then they would switch it up for the next message. So what they did, they had many different protocols, but like the one I'm going to pretend that everybody used is that they chose a random positions for the rotors and just write it down. So you just scroll the wheels randomly and you read those 3 letters, you write it down, and you use that to set the machine. And at that point, you choose a 3-letter message key and you key it twice. And I think originally they did this because they wanted to have a sort of like error correcting feature, because in the end of the day, they were sending everything through Morse. So they wanted to be sure that there were no mistakes into sending this temporary key, right? If you want to, and this is exactly one of the things that Polish cryptographers used to break this protocol. Yeah, we can talk about that later. Once you have this key, you generate this 6 letters, sort of like temporary key, and then you can use this to encrypt your message. And this is what you get. This is like one of the intercepts that got back to us. And you can see that at the top, you have this preamble with these like 6 letters, temporary message key. And you see that what they did is that they took the ciphertext and they just broke it into 5 5-letter blocks. And in this way, it's just easier to transmit for the Morse operator, right? And this is an example of a broken message, actually, like something that cryptographers were able to decode. So I think all the time I was reading this material, like what struck me was just how difficult this thing was. Like the Polish cryptographers, they started working on deciphering this. They didn't know the machine. They didn't know how the rotors was constructed. They didn't know the settings of the machines. And they had to come up with a way of understanding that. And it was like this life or death decision. So I think every time you're complaining about Kubernetes being difficult, you have to think about Polish cryptographers. I think it's a good life lesson of like what is really difficult. Anyways, that's the end of my rant about Kubernetes. Okie dokes. And at the other side of the world where you're receiving the message, you basically do the same thing. So you open the codebook, you set your own machine in the same way, same rotors, same settings, same buffer settings. Then, since in the message you have this initial setting and the 6-letter string, you just use them to decode the temporary message key. And once you have that, you can use that to decode the actual message, right? Okay, that was a long one, but I promise we're going to go through this later, like for real, so it's going to be fun. Okay, so yeah, I promised like this was going to be a programming talk, so I have to talk about programming a little bit as well, unfortunately. So Elm, it's this functional language. It's mainly used to create web applications. It's statically typed, so you most of the times write type signatures. It's like this lightweight version of Haskell, if you want. As other people have mentioned, it's a pure language, so there's only a managed way to run side effects. Normally, a function is always pure. Ultimately, it compiles to JavaScript, so you can run it on your browser. It's fun. You can go and check it out on elmlang.org. So, yeah, I don't really want to spend too much time on Elm. If we have time and if you have questions, we can take a look at the code, but it's quite simple. I think in total it must be 300 lines or 400 lines of code for the core of the Enigma machine. What I wanted to do is to focus on a couple of functions, right? Before we said that we have this journey of a letter inside the Enigma machine. So I just wanted to quickly show you how that looks like in the code, right? If we remember, we go from the keyboard, plugboard, wheels forward, old reflector, wheels back, plugboard, go into the light bulb. So this is how the function looks like in Elm. So we get an input character, we get the existing Enigma machine, and what we get back is an output character and the new Enigma machine. We need to get a new Enigma machine because every time we're pressing a key, the Enigma machine is rotating. So every time it's changing its state, right? Something interesting that I didn't highlight before is that if you think about that mental model of this bar, every time you press a key, the first thing which happens, like all these wheels rotate, and then the light bulb lights up on the sort of next configuration of the Enigma machine, like if you're keeping that key pressed, right? So this is exactly what the code does. It's like the first thing we do is we move the Enigma machine one step forward. Then we grab the left rotor, the middle rotor, and the right rotor, and we do exactly what we said. So we're going to take this input. This is a pipe operator. So it's just grabbing the previous value and passing it as argument to the function. We swap on the plugboard. We change it to a way that rotors can understand. We go through the right rotor. We go through the middle rotor. We go through the left rotor. We go through the reflector. We go backwards into the left rotor, middle rotor, right rotor, go back to the plugboard, and then we're done. So I think this is like one of these, like great examples of like how clean things can look like in functional programming, right? Like you're just changing this value, and there's no state. You're just like piping this value through, and I think it's quite neat. And the other thing I wanted to mention is that you can see that the stepped version is the next version of the Enigma machine. We saved it up here, and we're just going to return it. So the next time someone presses a key, we use this new Enigma machine, right? Okay, so this is the first. Am I out of time? 5 minutes, great. Okay, cool. So, okie dokes. So I wanted to, maybe I've done something bad because the computer is not responding anymore. Enter full screen. Great. So the other part which I wanted to show is like this stepping logic, right? We saw it in the video. So we can see that we check if the middle rotor has fallen into that little hole, which is called notch. And then we also check if the right rotor has fallen into that little hole. And if none of that is true, which is the last case, we always turn the right rotor, which is the fast rotor. That turns no matter what, right? But if the right rotor has fallen into that little hole, we're going to turn the middle rotor as well. And instead, if the middle rotor has fallen into that hole, we're going to implement that mechanical bug, which is the double stepping, which means that we're going to turn the left rotor, but we're also going to push the middle rotor, right? If we remembered before, we had this sort of like problem in the implementation, and you actually need to implement it if you want to be, faithful to the original design. Okie dokes, let's try it out. Don't have that much time, so hopefully everything is going to work perfectly. So I'm going to show you the Enigma machine. I have it here running. You can see there's, maybe I can make it a bit, it's fine, whatever. Okie dokes. So you can see like you have the rotors here. You can choose whichever rotor you want. You have some settings. And you have some plugboard configuration. So what we're going to do is that I've saved into TextEdit some settings for today, right? Today is the 28th, so according to this document, we should be using wheels 4, 3, and 1. So I'm going to do that. 4, 3, and 1. And the settings of the wheels for that day were 3, 4, and 22. So we're going to do the same. 3, 4, and 22. Perfect. I'm going to empty this input. So basically now, like, the thing is, you have to choose a random initial position. And this is something that historically happened because people are very lazy. So the German operators used to choose the name of their city or the initials of their wife, of their girlfriends as the initial setting because they couldn't be bothered to come up with a random thing. So I'm going to put Elm here as the initial random position. And at this point, you choose the temporary message key. I'm going to choose Mike and type it twice. And you can see that the output is quite different, right? Like it's like this thing. Oh, I forgot to set the, I also saved the plugboard settings. So I'm just going to paste them in. Cool. You can see like this is like the beauty of the Enigma machine that we know that M and M are the first and the fourth character, but in the output, they're completely different ones. This is like the beauty of having this polyalphabetic substitution cipher. Anyways, we write down that the code is this RG whatever, and now we're ready to send this thing. So I'm going to set this temporary message key, MIC, and I'm going to send a message in German, which is something that people used to send, which means nothing to report. So they would specifically target outposts in the middle of nowhere. They knew nothing was going to happen there, and they knew that the plain text was going to be nothing to report, and they would use this information to try to break the settings of the machine for that day, right? So this is keine besonderen Ereignisse, which means nothing to report. Beautiful. And this is the result. So basically, we know that if I make a little space, we know that, can I make it a bit bigger so you can all see? Yeah, that's great. You can see like this would be the message that you send over Morse. You said Elm, is like the initial random thing. This is the setting, and then the message. So on the other end of the world, whenever you want to receive this, you set the random setting first, Elm. You key in the 6 letters like temporary code, which is this RGOYF. And you can see that the machine has this beautiful property that using the same settings, it will transform plain text into ciphertext and ciphertext into the same plain text. It has like this beautiful like mathematical property. And this is actually guaranteed by that piece of metal, the reflector that we talked about before. Like this is what gives us this really nice property to the system. And in this way, you know that the temporary message key is MIC. So we're going to set it in the machine, MIC. And now we can take the ciphertext and plug it back in. And you see, this is the output, like keine besonderen Ereignisse. Am I out of time completely? Yes, yes. So I think the only thing which I've left here is I've added some links. So if you want to, okay, so I've written all this down. It's okay. So I've collected a lot of resources about the Enigma machine. There's that beautiful YouTube video. There's some really, really nice resources written by people that have worked in Bletchley Park. And I think they wrote it maybe 15 years ago. So the website is not the most beautiful website you can ever see, but I think the information is really nice. And there's also emulators, which are really beautifully done, you know, like with all the fancy 3D animations. So if you're more interested, you can look at that. I've added the links to stuff. Yeah, I'm done.
That was fantastic, thank you. Does anyone have any questions? Oh, do you want to?
It was a lot.
Here we go.
Oh.
Oh, yeah, and also we've got, Victor's going to be walking around with the voting board to rate the talk rather than at the door. So please poke it when he walks past.
Will you tell us how to crack it next year?
Yeah. So that's super interesting, actually. It's like, if you think about it, like this encryption thing was devised in the 1920s, but the actual key space is so big that even with modern computers, we can't brute force it, right? Like the key space is just too big. So it's like one of those examples where math is just too good, right? Of course, just in the same way as the Polish cryptoanalysts and the British cryptoanalysts broke the code, we can use similar techniques in breaking the Enigma cipher. But yeah, I think that's the argument for the next talk. And this is something I actually wanted to mention, because if you watch the movie, The Imitation Game, I think they don't mention at all the contribution of Polish cryptographers to this thing, which I think is a big shame, because from 1932 till 1939, for 7 years, Polish cryptographers at the Polish bureau, like Cipher Bureau, they were able to basically break Enigma without ever seeing the machine, just by being really smart. And then in 1939, just before Poland was about to be invaded, they ran away and they gave away all the secrets to French and British intelligence agencies. For example, a very important Polish mathematician was called Marian Rejewski, and he actually managed to run away to Britain, but they didn't want him to work on this stuff anymore because they were afraid he was going to be a spy. So he was basically stopped from contributing to the work that he pioneered, which I think was quite annoying. And even I think the British cryptanalysts, they try to give some credit. For example, the Turing machine was called the bomb, and it's a homage to the Polish work, because in Polish, the device they came up with was called bomba. So that was, a way for them to give Polish people credit. But yeah, I think, there's like a lot of things which are super interesting. And in the movie or even in the official literature, they didn't really give much credit to them, even though they did all the work, really. Like the British people and the French, they didn't know how to break the Enigma machine. They were, stumped. And it was only thanks to the work of Polish people that they were able to do so.
Do we have any more questions? We've got 1 minute.
I think there's a question down there.
Oh.
Yeah.
Very close.
Do you have an Enigma machine, like a real one?
There's a park called Bletchley Park in the United Kingdom, where there used to be like sort of like counterintelligence action in the UK. There used to be at peak 10,000 people working there, like 6,000 men, 4,000 women, and there are original Enigma machines there. If you search on YouTube, there's one crazy person, I'm not sure from where, that decided to 3D print a working version of the Enigma machine, and it is working, I saw it. I think he posts video every couple of months, so I'm not sure if he gave up, if he's like, going through some mystical crisis, but you can follow him if you just search 3D printed Enigma machine. And also every once in a while one comes up, maybe it's like someone is hiding it in a basement or in an attic, and they sell for like $50,000. So if you're really interested, you can buy one, and if you're rich, of course. But yeah.
That's great. Thank you very much, Ju. That was extremely entertaining.